Today we're going to discuss the principle of indifference, which is the subject of chapter number 3 in the book. Let me just remind you that we use capital V to denote the value of the game. A bold lowercase p is a strategy for player number 1. A lowercase bold q is a strategy for player number 2. The main theorem in this chapter is the so-called equilibrium theorem. Now the setup here is as follows. We have an optimal strategy for player number 1 with the property that the first coordinate is positive. So there's a positive likelihood that this player is going to choose the first row in the matrix. Then we have some optimal strategy for player number 2 with no conditions. Then this equation holds. What does this equation really say? Notice that you have A1J there. These are the entries in the matrix in the first row. So what this equation really means is that if player number 1 chooses exactly one row, the first row in the matrix, and player number 2 is using an optimal strategy, then we obtain the value of the game, which is paid from player number 2 to player number 1. We can use this equilibrium theorem as follows. Here's a simple game, which we've seen before. It's called the game of odd and even. The two players call out simultaneously either the number 0 or the number 1. We calculate the sum. If the sum is even, it's paid to player number 2. If the sum is odd, it's paid to player number 1. So there you see the game matrix. Now if we want to use the previous theorem, we have to make some assumptions. And the assumption we're making here is we're going to assume player number 1 has an optimal strategy where there's a positive likelihood of choosing either row. So we can apply the previous theorem both to row number 1 and to row number 2. Now, if he chooses row number 1, then the sum on the previous page boils down to this simple equation. P2 equals V, the value of the game. If he chooses the second row, then we get P1 times 1 plus P2 times minus 2. That's this equation. So now we have two equations, but three unknowns, the P's and the V. But we have one more extra equation that we can use, and that's the fact that we're dealing with probabilities. So P1 plus P2 equals V. And now we have a third equation, and this will allow us to solve for P1, for P2, and for V. So here is an example how we use the previous theorem. Now, the chapter also goes into non-singular game matrices. So what's happening here is, as always, there's this matrix associated to the game, like we saw previously, and it's called the game matrix or the payoff matrix. And what happens in this chapter is that if the matrix is non-singular, remember non-singular here means the matrix has an inverse. What does that really mean? It means that there's another matrix, usually denoted a to the minus 1, such that if you multiply the matrices together, you get the identity matrix, and the order does not matter. You get the identity matrix. And what happens here is that you can show that you can get a strategy, an optimal strategy for player number 2 by summing together all the values in the inverse matrix, taking 1 over that, gives you a number. You multiply this number by all the entries in the inverse matrix, and then you take the product with a vector that's called 1 And this vector is the all ones vector. It has 1 in every coordinate. So again, if you have a matrix with an inverse, you can do this. It's kind of a machine that you plug into, and this gives you the optimal strategies. And I wrote down the optimal strategy for player number 2 here. There's something similar for player number 1. And furthermore, this number here is the value of the game. So you get optimal strategies and you get the value of the game. And the chapter ends with talking about special cases where you can use this. And one of them is so-called diagonal matrices. And these are particularly nice matrices. And they look like this. You have entries on the diagonal, and zeros everywhere else. And here is a really simple criterion for whether the matrix has an inverse. You have an inverse for the matrix if and only if all the entries on the diagonal are not 0. And you basically apply the methods you learned from the non-singular matrices to this special case. And that's it for today.